Today's presentation will focus on identifying and resolving inefficiencies in I/O systems. Now, this is just one part of this complete performance optimization workflow that I'm showing here. The workflow begins by profiling your application to identify hotspots. Once you've identified those hotspots in the application, you focus your optimization efforts on one particular aspect of the application. In this case, we're going to focus on file I/O. After you've improved performance to an acceptable level, again, profile your code to quantify the gains and refocus your optimization effort. The 50x, 10x, 5x, 2x labels that I'm showing on the hotspots, those aren't speedups. Those are potential slowdown that could be realized by making a small mistake in that particular aspect of the application's performance. Or to put it another way, it's not uncommon for a small mistake in how the application uses the file system to be 25 times more damaging to the application's performance than a small mistake in how the application uses the CPU. So just what do we mean when we say I/O system? Well, in this case, I'm talking about the high-performance, massively parallel file systems that are available in most HPC centers. And these are optimized for parallel computing applications specifically. These parallel file systems are physically composed of thousands of disks, a network interconnect, and server processes in different roles. For example, you might have metadata servers that provide information about the data, but not the data itself. In these systems, multiple network hops are usually required to perform any I/O operation, so latency will be a bit higher than what you're used to on the local file system. And that means you should avoid small sequential operations like file open and close or sub-block writes. Now, the latency of high-performance parallel file systems that you'll find in your HPC center, it's typically less than the latency of the parallel file systems you'll find in something like a throughput computing center. But the expensive InfiniBand interconnect that you've paid a lot of money for to get low latency can quickly go to waste if you don't optimize your code to avoid high latency operations. The true advantage of these high-performance parallel file systems is their tremendous bandwidth, because they can perform many I/O operations in parallel. In general, you'll get the best performance by preferring parallel operations on large chunks of data. Now, all this complexity means that portable performance analysis tools are an absolute necessity. Performance fluctuations are normal, so without tools, you're going to struggle if to know if a performance problem is occurring in your application, in another user's application, or even in the I/O system itself. So why does I/O have such a huge impact on performance? Well, on virtually all HPC systems, I/O is inherently a shared resource, not only between all parallel processes in your particular application, but also between all the applications on the system. This means that I/O performance optimization in your application has the potential to improve performance system-wide. Does your sysadmin seem to hate you? If so, then you probably have an I/O issue in your code. Also, file system I/O occurs at the slowest tier of the memory hierarchy, which is logarithmic. So small mistakes at this tier are orders of magnitude more expensive than mistakes at higher tiers. But this also means that a very low effort optimization can have an enormous payoff. Another reason I/O optimization is so important is there aren't very many tricks for getting around the data requirements of most HPC applications. This is an example from NASA's GEOS model from the Global Modeling and Assimilation Office. This chart compares observed values of carbon monoxide in the atmosphere over Denver, Colorado, with predictions from GEOS running at two different resolutions. The blue line shows 200-kilometer resolution, and the predicted values are not very accurate. But if we increase model resolution to 12 kilometers, as shown by the red line, then the predicted values begin to match the measured values fairly well. The 12-kilometer run requires almost 300 times more data than the 200-kilometer run, so we'd like to see if we could reduce the data requirements of the 12-kilometer resolution run. Unfortunately, if you look at the purple line, you'll see what happens if you take the 12-kilometer run and downsample that data to 200 kilometers. In this case, downsampling the data dramatically reduces model accuracy because areas of high and low carbon monoxide concentrations have been averaged. This means we really cannot use lossy compression like downsampling when storing the high-resolution model checkpoints and results. The full resolution results have to be written to disk, and this places enormous strain on the I/O system both at runtime and during post-processing. So we've seen one example of how the I/O requirements of an HPC application really cannot be reduced. And this leads to I/O dominating the application's performance curve. But it's generally true for the majority of HPC applications. Furthermore, many applications perform very few floating point operations per byte, and this low computational intensity means a lot of data is required to advance the model state. I/O must occur throughout the application's runtime in order to generate acceptable results. Checkpointing and restarting is another consideration for I/O optimization because applications must periodically dump the model state to the file system in order to provide resilience against system failure. You also need checkpoints to have reproducibility of results and state provenance, some sort of history of how the final answer was generated. Now, these checkpoints will cause all the nodes in the system to write to the shared file system resource at the same time, which can potentially flood the system with I/O requests and create a severe performance bottleneck if not handled correctly. Checkpoint operations need to be considered very carefully at scale. And finally, data post-processing puts an enormous strain on the I/O system by loading saved results and saving visualizations and charts and reports, etc. back to the file system. Since we typically cannot reduce an application's I/O requirements, how do we improve I/O performance? Well, the first step towards optimizing your application's I/O performance is to understand your I/O system. Now, there are a great many different I/O systems, so don't make assumptions about what's available in your particular machine. Especially if you're porting applications between multiple platforms, go read the documentation and find out what's mounted and available. Your typical POSIX file system can be hosted by a variety of storage systems, anything from NFS, Lustre, GPFS, BGFS, even Ceph, which is really not a high-performance file system per se. It's usually used for object storage. Ceph provides a POSIX interface as well. There's also a lot of variety in the hardware infrastructure used to provide the storage service. So you should be familiar with your system's network fabric and know a little bit about the system topology. For example, are there dedicated I/O nodes? How many compute nodes are served by an I/O node? And are there infrastructure optimizations that you can take advantage of? Many HPC systems provide small local file systems and in-memory file systems like dev/shmem that you can use for scratch files and temporary files. Also, burst buffers and non-volatile memory are becoming pretty commonplace in HPC. And while it's important to understand what's available in your I/O system, there's not too much you can do about it, right? At the application level is where you have the most control. So ask yourself, what are the I/O characteristics of the application? Is I/O dominated by read or by write? Is the data accessed sequentially, randomly? Does the application do I/O in bursts, or does it stream data through the disk to the CPU and back again? And how exactly are you performing those I/O operations? Are you using standard library calls like read and write to manipulate files in the POSIX file system? Or are you using a parallel I/O library, so maybe MPI-IO or HDF5? And there are lots of non-I/O operations that can impact the performance of I/O. For example, does the application attempt to overlap file I/O with internode communication? Remember that this parallel file system is going to use the network interconnect, so communicating and performing file operations may in fact compete for the same resources. Have you designed some processes to perform I/O on behalf of others so that the data will need to move between nodes before it can be written to disk? Now, there's advantages to this, but it can become a bottleneck. So let's have a look at some possible I/O schemes you might encounter or implement. So a more sophisticated way to approach the problem is to treat parallel I/O like shared memory and use a library, something like MPI-IO or HDF5. These libraries have knowledge of the underlying I/O system and can implement more advanced I/O schemes, like the N-to-1 scheme, where input and output files are operated on concurrently by many processes. The scalability of this approach depends on your I/O system and the access pattern of your application. There's also an end-to-end scheme where gangs of processes will cooperate to write sets of files. And you can use this approach to balance the responsibilities between the application and the I/O system. This is also a good way to mirror the physical infrastructure of many HPC systems where a single I/O node serves many compute nodes. If you select an appropriate gang size, you can easily balance the load across the different I/O nodes. Now, there's no clear best approach for parallel I/O. You should also consider how the data in the file system will be consumed after it's been written. It could be the case that it's worth sacrificing some time in slower I/O at runtime to generate appropriate metadata like HDF5 descriptions for different parts of the data, and that will make it easier for another program to reconstitute the data set when it's written. So for example, it's all too easy to wind up with a binary file written by MPI-IO using a certain number of processes, and then find that that file cannot be easily opened with a different number of processes. So consider all your available options. Think about native POSIX, MPI-IO, HDF5, NetCDF, Audios, all the various high-performance parallel I/O libraries that are out there, and see which of these is going to fit your problem best. So we've seen that I/O optimization must be done at the application level, and the next step is to understand the application's performance. And this is the profiling step that I started with in the iterative optimization workflow. Now, there are many profilers out there, and they all have their own unique features and strengths and weaknesses, but I'm going to focus on ARM's map profiler, which is found in ARM Forge. ARM Forge is a commercially supported cross-platform performance engineering toolkit that consists of the DDT debugger and the map performance profiler. Forge focuses on usability, scalability, and cross-platform applicability. It's designed from the ground up to scale to many thousands of processes, so it's found on a large portion of the top 500 supercomputers and as well as many unranked supercomputers and compute clusters. So there's an excellent chance that it's already installed on your HPC system. Forge is also cross-platform. Now, I know it's called ARM Forge, but ARM is just the brand name here, right? Forge runs on x86, it runs on Power, it works with GPUs, as well as ARM architectures. ARM is just the brand name. It doesn't refer to the instruction set or any feature of the computer architecture. It's just the ARM Forge is the name of the product, right? It works on every major HPC architecture out there. It's definitely a cross-platform product. Now, I'm showing some pictures of MAP here, which is part of Forge. MAP is a lightweight profiler designed for scalability and ease of use. There's a lot of I/O profilers out there. Some well-known ones are like Darshan and Alexis. These are good for profiling I/O, but MAP also enables an intuitive understanding of the application's performance, not just in I/O, but also MPI and compute regions. So this is a good way to see the interaction of different aspects of performance in your application and how they can result in poor I/O performance. And using map is extremely simple. Typically, you just put the word map in front of your application's command line and the program will do the rest. For example, I'm showing here how you might use the -profile flag to generate a map profile for an MPI parallel application with 48 ranks. This example application will run to completion, then write a file with a .map file extension that contains all the gathered performance data. And then you can use the map GUI to open the file or even use the map remote client to access the file on a remote system. And that's personally what I do. I typically use the remote client as I find forwarding X11 over SSH to be extremely slow. But the remote client is very responsive, even under fairly adverse network conditions. So I find that's a really good approach. Now, a product related to ARM Forge is the ARM Performance Reports. So Performance Reports provides a high-level overview of your application's performance characteristics, including notable features of I/O performance. And you can use the output from ARM's map profiler as the input for performance reports. So you kind of get your performance report for free if you're using map. This is free in the effort sense, not in the money sense, right? Talk to our salespeople. But Performance Reports is a great way to improve your high-level understanding of I/O in your application after using map as your frontline sort of first-pass profiler. So let's get into some examples here. Our first example is going to demonstrate how important it can be to choose the appropriate file system when running your application. This is the initial profile of Hydro-C, which is compiled with Intel compilers and running on an x86 system. The profile shows that over 16% of the application's runtime is spent writing small intermediate files in an end-to-end I/O pattern. Now, surprisingly, only 5% of the runtime is taken up by actually writing the data. The remaining over 9% is spent entirely in opening and closing files. So in MAP, you can select a portion of the application timeline to focus your analysis on a hotspot. I/O is shown in brown, so if we focus on the area of the timeline with a lot of brown, we can see what I/O calls are most expensive and why. In this case, file open operations are responsible for 17.5% of the I/O time in this selected region, and file close operations were responsible for over 11%. Open and close are small serial operations. The latency of our parallel file system is simply too high for these small intermediate files. Since we're using an end-to-end I/O pattern, a local, non-parallel file system is a better choice. And in this case, we can even use the in-memory file system mounted at /dev-shmem to improve read and write performance, as well as file open and close performance. Using dev-shmem reduces the application runtime from about 3 minutes to just 1 minute, and brown disappears from the timeline almost entirely. If I again focus on the code region where we previously saw the I/O hotspot, we now see less than 1% of the application's runtime is spent in I/O. Now, a gain of just 2 minutes may seem trivial, but note that this application was exhibiting this I/O problem at just 16 MPI ranks. At scale, this small gain of 2 minutes easily translates to hours, even days of runtime reduction. So this is a very, very important result. Now, for comparison, here are the same results, but using the ARM performance reports to show I/O performance. You can use the map output files to generate these reports, and this will help focus your optimization efforts a little more, or give you a higher level aspect of the performance. This report shows that before optimization, our effective process write rate was just 1.38 megabytes per second, which is pretty low. After optimization, the report shows that the effective process write rate has increased to 57.5 megabytes a second, which is a performance gain of over 40 times. You can see how that would really pay off at scale. I'm going to move on to a second example now that will show how the timeline view in MAP can highlight I/O issues in your application. Now, this application writes 3 visualization results, and we would expect each of those writes to be cheap and take approximately the same amount of time. However, after profiling the application, we can clearly see on the application timeline that the writes are fairly expensive and that the third write operation takes much longer than the previous 2. I'm just going to zoom in on the timeline a little there so you can get a better look. If you take a closer look at the disk write transfer data, you can see that our maximum write rate is less than 14 megabytes a second, which is far below what the system is capable of. The source code view in MAP will show us that we're using Fortran write statements to output data in ASCII format, and we're using an end-to-end scheme. This is problematic for 2 reasons. First, ASCII is a bulky format compared to binary data, which means we must write many more bytes to disk to save the same amount of data. And secondly, the end-to-end scheme based on Fortran write statements will have no knowledge of the underlying I/O system, so it can't take advantage of striping, aggregation, or other useful features that the I/O system might provide. So the solution was to replace this naive end-to-end approach with calls to HDF5. Now, this had a lot of clear benefits. Not only does the I/O behave as expected, but it's also much more efficient, and the application overall is running faster. Instead of writing ASCII files, HDF5 uses a binary format. In this case, it means the output files are smaller and the data are more precise. The data are also described with headers, so that if you needed to reconstitute this data in future, it'd be much easier. Our maximum transfer rate is now 5 times higher with HDF5 than it was with ASCII, and the 3 I/O regions that I've highlighted here take approximately the same amount of time, which is what we expected. Now, there's still a lot of room for improvement. Time spent in MPI barrier isn't fully balanced yet, but communication optimization and load balance is another webinar, so tune in another day. My final example shows how you can use MAP to measure not only your application's I/O performance, but also the performance of the I/O system itself. We're going to look at how you could use MAP to look at the Lustre metrics on Archer while running the iPic3D code on 1K processes. iPic3D is a C++ code with MPI that uses 3 different I/O approaches. It writes simulation results as VTK binary files, reads and writes checkpoints as HDF5 binary files, and saves field values using collective MPIO to a single file. A tool like MAP is vital to understanding and improving the performance of such a code when executing on a Lustre file system. MAP will show you Lustre read-write rates, as well as metadata operations like file open and close. And this is a powerful way to differentiate between application-level I/O issues and system-level I/O issues, and explain run-to-run variability. We're going to be measuring data from both the system and the application level. At the system level, MAP can read Lustre log files to observe read, write, and metadata operations recorded from each Lustre client. Aggregate I/O and bandwidth statistics are also available. And then finally, the system scheduler logs can be used to bracket the Lustre events by application start and end times. The Lustre system isn't aware that MAP is profiling the application, so it can't inform MAP directly when to start and stop recording data. So we use the system logs to match the data streams. At the application level, we have all the same data we've already seen: I/O bandwidth, instruction classification, and the ability to identify different I/O phases within the application timeline. Open MAP's Lustre metrics to see the application timeline, including I/O performance, alongside Lustre's system-level performance. In this case, we see that not all the application I/O regions directly correspond to a spike in Lustre activity. For example, local file system operations are not going to involve Lustre. However, using HDF5 to write checkpoint restart files does correspond to a spike in Lustre write rate. At the beginning of the model run, every MPI rank opens and reads a file in an in-to-end communication pattern, and the effects of this on the Lustre file system are clearly visible. Now remember that this application involves 3 different I/O schemes. We can focus on a particular region of the application timeline to better understand the I/O characteristics of each I/O scheme. In this case, writing field values as VTK files shows a low write rate in Lustre. Focusing on the part of the timeline where the checkpoint restart file is written, we can see that not only does HDF5 realize an almost 2 GB per second write rate, there's also some overlap between MPI communication in the calculate field routine and the I/O operations in the write restart routine. And finally, this code region shows how different I/O schemes may in fact overlap at runtime across many MPI ranks. There's overlap between the VTK file write operations and the write restart operation. Achieving this kind of performance with a handwritten, naive I/O scheme would be very challenging, so I/O libraries that have knowledge of the underlying I/O system are usually the right choice. In conclusion, I'd like to point out that if ARMForge is not already installed on your system, you can try it for free by going to arm.com/HPC. Trial licenses enable all the HPC products and all the features. With Forge Professional, you'll get up to 64 MPI processes for one user, but it does include all the features and all the architectures. Now, by all architectures, I'm saying that ARMForge runs on x86, Power, ARM, and it'll even show you GPU performance. If you happen to be on an ARM-based system, you can use the same trial license to learn about ARM's HPC compilers by looking at the ARM Alenia Studio package, which includes Forge as well as our C, C++, and Fortran compilers. So visit the website, download some trials, have fun. Thanks.
We're now going to open up the panel for any questions. As stated earlier, if you can post any of those questions via the questions panel, we'll obviously try and answer those for you now shortly. Over to you, John, if you see any questions coming through.
Thanks, Mark. Yeah, let's see if I'm coming through all right here. Just getting my questions panel open. So, okay, first question. How much effort to switch from the Fortran write statements to HDF5? Well, Okay, so there is some effort, but so it's not a straightforward, find and replace in your operation, especially because we're changing the data format from ASCII to binary, and HDF5 can be self-descripting. So it is a straightforward transformation, but it will require a little bit of software engineering, and of course, always a good idea to save your results before you get to work so that you have some baseline to compare to afterward. Second question, is this webinar recorded? Yes, the webinar is recorded. We'll make the video available on the ARM website, as well as I think it's going to be linked in other locations. Mark, can you summarize where all the materials will be available?
Yes, yes, thank you, John. A very good question as well, actually. So yes, as John mentioned, shortly you will receive an email which will give you a link to the recording itself. It will also be on the ARM YouTube channel, and there'll also be an on-demand site within ARM network itself. But yeah, but for everyone who has registered today, you will receive an email in the next, I would say probably next week now, not this week, and that will give you a link to this recording. Okay. Okay. I don't know if can you see any more questions coming through there, John?
How does MAP compare to Mistral? Okay, so this is from Alexis, right? So actually, ARM and Alexis work together. We even have a custom metric for Mistral in MAP. Probably the key difference between these two things is that Mistral is a system-level I/O profiler, and of course, Alexis build themselves as like the I/O profiling company, right? So they're really highly focused on different types of I/O profiling you can do. MAP is a really good first pass profiler to identify I/O hotspots in the application and see how those hotspots interact with other parts of your code, or how the performance of those hotspots, I should say, affect the performance of other parts of your code. But Mistral would monitor application I/O at the cluster level, right? I think they even have some load balancing features in there. So both very good tools, but slightly different use cases, although they do in fact work together. Okay, I've got a few more questions here. Will the slides be available for review as well? Yes, we will definitely make the slides available. Question, what tools do you use for profiling? Do you have any key points on the profiling? Okay, well, I've just shown you the MAP profiler. MAP is a very good tool for profiling. That is exactly what MAP does. Most of this presentation was presenting the MAP profiler, so that's where I would say start with. I also use Tau. Tau is a good profiler. I use Scorpy. I've been known to use even some simple lightweight tools like MPIP. But really, it depends on what you're trying to achieve. The reason there's so many profiling tools out there is there's so many use cases. What I typically recommend is use a lightweight, high-level tool like MAP for your first pass profile, and then based on that first pass profile, pick up some heavyweight tools, maybe the NVIDIA profiler if you want to drill into a GPU section, or maybe Scorpy if you want to generate something like an OTF2 trace and view it in Vampire. So it really depends on what you're trying to achieve, but MAP is always a good starting point. Do you have info on webinars for ARM HPC processors? And that's an interesting question because first, let me see if I can clarify ARM's role here. ARM provides intellectual property that our partners license. So companies like Cavium, Qualcomm, Fujitsu, these people license ARM and then they build the HPC processors, right? So ARM, in fact, does not build the processor. So when you say ARM HPC processor, there's no one product that I could talk about. If you want info about ARM, about high performance computing processors that use ARM intellectual property, you should go to the partner companies. So I would recommend going to Cavium to find out about the Thunder X2. Go to Huawei to find out about the high silicon processor. We'll go to Qualcomm to learn about their processors, right? But ARM is not going to provide webinars about the processors themselves because we don't make them. You'd have to go to the company that makes the processor.
Okay, any more questions? Oh, I think we just had another late one just come through. Over to you, John. You can probably take that one from there.
are there specific features of the ARM processors that address this issue, the I/O issue? So ARM, okay, again, there's not really such a thing as an ARM processor, right? If you want to talk about a particular partner's processor, then the answer is yes. So let's pick up a particular partner. Let's say Cavium, right? Now Marvel, right? If you look at the Thunder X2, it has a lot of memory controllers. It has a very excellent performance when it comes to memory-bound codes. So the ability to move data through this processor is really competitive. It is one of the distinguishing features of it. In fact, DDN, go check out DDN. They have some evaluation materials for Lustre running on ARM processors. They actually looked at the Thunder X, the first generation Thunder CPU from Cavium, formerly Broadcom, right? There's a slide deck out there from DDN that'll show you some performance evaluation of Lustre on ARM using this older CPU from Cavium. And the numbers are pretty good, right? So are a little lower than we'd like, but reads are pretty good. And the Thunder X2 just improves on those results. So that'll give you a good idea of some of the advantages that are available there in the Cavium specific processor.
Okay, I think that's about it, John. Okay, I'd like to thank everyone for joining us today on this webinar event. As John has mentioned before, there are other webinar materials in the series which you can find on the ARM YouTube channel. And as stated earlier and previously, you will be all receiving an email which will give you a link to this particular recording. I see that somebody has asked about slides as well. We could also potentially make that available too. But in the first interim, you should receive these, as I say, probably sometime next week. Yeah, just like to thank everybody for attending today, and please look out for the next in the series. And I don't know if that would like to sum that up as well, John.
No, that's great. Thanks very much, Mark. I hope to see you guys again in the next webinar.
Okay, thank you, John. Thank you everyone for attending.